Bismillahirrahmanirrahim. Today, inshallah, we shall talk about segments and proving segment relationships. That is, which ones are congruent, which ones are not congruent, etc. And as an introduction, first we have a very important postulate. And anytime we have a postulate, a theorem, or axiom, etc., we have to make sure that we understand and memorize it because these will recur again and again. So I have stated over here what's called the segment addition postulate. And some of these in the beginning may seem very intuitive and easy for you to say, well, everybody knows that type of a thing. But, it's like A equals A. I mean, reflexive property of equality for real numbers. Everybody knows that, you say. But that's true. These are simple things that we kind of take for granted. But, it's like saying a little kid, A, B, C, D, E, F, G, H, I, J, K, all says that's A, B, C, D. Everybody knows A, B, C, D. That's like, of course, A, B, C, D is easy, but look what you can do with that, right? The same thing here. Some of these initial postulates and theorems and properties are very intuitive and easy, but they allow us to build an edifice of logic, build a system of logic where we actually derive some very complicated and elegant proofs in the future. So nevertheless, anytime we see any of these postulates, properties, and theorems, we have to make sure that we understand them and be able to articulate them or enunciate them in a most precise, concise manner. So here's a segment addition property, or a segment addition postulate. Now, if you recall, postulates are those statements that we accept to be true, but we cannot prove. Now, this postulate is a simple one once understood. It allows us basically to say that if you have two baby segments, you can add them together to give you a big, large segment. Let's read what it says. It's a if-then statement. It's actually a little bit more than if-then statement. We'll see. If A, B, and C are collinear, so I've drawn a segment over here, A, B, and C. It's given here that the A, B, and C are collinear, that are on the same line. If this is the case, then point B is between A and C. So point B is between A and C if and only if. Now, first appreciate that this is a conditional statement, if and then. So, conditional statement, if you recall, is followed by a hypothesis, and then is followed by the conclusion of that statement. So, this is no ordinary conditional statement either. So, this is if A, B, and C, then point B is between A and C, if and only if. And if you recall, this phrase is very specific to imply that this is a biconditional statement. That is, it's the original conditional statement and its converse are true. So P, if P then Q, and if Q then P, like this, or we can just say like this. So this is a biconditional statement. Okay, so segment addition postulate is a biconditional statement, and it says that if you have 3 points like this on a segment A, B, and C, then B is between them only if AB, the measure of AB, that is from here to here, that's going to be the measure of AB, right? If the measure of AB plus the measure of BC, if you add to that the measure of BC, if you put them together, right? And if you put them together, what you get is AC, the whole thing. If this plus this equals over here, that's AC. So if you, let's say this is 5 and this is 7, if you take 5 plus 7, and that gives you the measure of AC, and sorry, I meant to say 5 plus 2. I'm not thinking ahead over here. If this is 5 and this is 2 units long, and if AC is 7, then you can be sure that B is between A and B. Now, as I said, you might think that this is kind of very intuitive, right? Well, that's obviously that's going to be the case, but there's a little bit more elegant a challenge behind this particular question. For example, if I redraw this segment and I put A over here and I put C over here, and let's say imagine B is not on this line. It's tiny bit high, but I've kind of made it like tiny bit high like this, but imagine it is like almost to the point that you can't even tell if it's really on the line or not on the line like that. but so that at least that you understand, I put this slightly higher than it is drawn here. So let's say if this is AB and let's say this is AC. Now clearly in this second scenario, this is AB, that's point B over here, and so let me put tiny point B right there, and this is AB and this is BC. In this case, if you add up AB and BC, they're not going to equal to AC because it's a little higher. In fact, it'll be a little bit bigger than AC, right? So it's suggesting that the way you know that a point is between two other points is that if you take the two baby segments, if you add them together, you get the measure of the big segment. So how do we know that the point is between 2 points, and if they're seemingly on the same line? Is if you add the two baby segments and you get the measure of the big segment, then they are all on the same line. If that's not the case, if you add AB and BC and it's bigger than this segment over here, let's say, then B is not between A and C on the same line. Okay, so this postulate seems intuitive, but it's just a very tricky and profound concept, because in real life you might not be readily able to tell if a particular point is in between two other points or not. All right, so let's now, with that understanding, let's read this segment addition postulate again. It states, if A and B and C are collinear. So if this is the case, if they're on the same line, you can be very sure, you can be very confident that if they're on the same line, then B is between, it has to be between A and C, and if and only if you take the two baby segments and add them together, get big segments. So if I have another point over here, for example, point D, if all of them, A, D, and C, if A, D, and C would be collinear, if they're collinear, only if and only if they would be, if AD plus DC is equal to AC. All right, so this tells you how to determine whether a point that's on a segment that seems like on a segment is actually on the segment. Now, the converse of that is if you take two baby segments, the converse of that is if you have something like this, if you're given that AB plus BC is equal to AC, if you're given this particular scenario, then you can be confident that B is between A and C, because that's the only way that this will be true. So if you take two baby segments, if you add them together and you get the same as the big segment, then you can say B is between them. And if you have if 3 points are collinear, then the two baby segments will add up to give the one big segment. So let me read this segment addition postulate one more time so we can memorize it in its proper form. The segment addition postulate states that if A, B, and C are collinear, then point B is between A and B if and only if AB plus BC is equal to AC. That is, if 3 points are collinear, the 3 points are collinear only if the two baby segments add to give the one big segment. Now, this segment addition postulate allows us to do many things. It opens doors for us to prove many relationship between segments, and that's what we shall try to do in the next couple of examples, inshallah. Okay, so here we have our first question. Let's read. So this one states, the given, so this is a given information, given CE is congruent to FE. So when you're given stuff like this, we can actually mark it on the diagram that's given to us to help us understand and formulate a plan. So we're given that CE, that's this little segment, is congruent to FE, and that's the little segment here, this point being E. Now here we have to assume that the E is the intersection of CD and FE. Well, why do you say? Well, isn't it obvious that E is the intersection of the CD and FG? Well, not necessarily, because watch, I could have this little segment here, and they kind of go in a distance, and I could have this one over here and that one kind of go like this. So how do I know that they're not like, you know, going in different directions like that, right? But they don't, because here from this diagram we can assume that E is the intersection of these two bigger segments. So there's certain things that you can assume in a diagram, and there's certain things that you cannot assume in a diagram. In this diagram we can assume that E is the intersection of these two longer segments. Okay, nevertheless, so we have CE is congruent to FE. And then we are also given that ED, that's this segment, is congruent to EG, which is this segment over here. All right. So we're given that this is the information that's given to us. Okay. So those segments are now we're asked to prove that CD is congruent to FG. So from this information we're asked to prove that this big segment is congruent to this big segment over here. Now, to you that might seem like, boy, that's obvious. Well, we can't use that's obvious as a proof for things in geometry, but we have to actually use the properties, theorems, and postulates that we have learned to actually prove that in a logical fashion. Well, how do we go about proving this? Okay, well, the first thing we do is we write our two-column proof, and here we're going to use a two-column proof. So I'm going to draw out my two columns here, and I'm going to label the two columns. If you remember, in the first column, here we go, statements. And in the second column, we have the reasons for those statements. All right. And when in doubt, you begin with what's the given information. So first, given where CE is congruent to FE. So that's given to us. And at the same time, ED, you can write both givens in the same line if you need to. So ED is congruent to EG, like this. Okay, so the reason for this is that this is given information. So what I have stated so far, so I said CE, that's this, is congruent to this. See, those two baby segments are congruent. And the second piece of information says that ED, all right, is congruent to EG over here. Now, how do we know how to go about this proof? Well, the idea being that the diagram and the given information should kind of like trigger some memory on postulates and theorems that we can possibly use to prove this. Here you see two baby segments, and then we're trying to prove that the big segment is going to be congruent. So which postulate is it that we know that says that two baby segments, when they added to give one big segment? Well, he just did this over here. That was the segment addition postulate. So here we should say, okay, we can use perhaps a segment addition postulate to prove this particular case to be true. So that's kind of like our approach. So you have to have a plan in proofs to go forward. So I'm going to try to use the segment addition postulate to prove that's to be true. Now, mind you, the segment addition postulate applies to one segment. That is, if this baby segment plus this baby segment, if you add it together, it'll give you the one big segment, right? So it's not about two segments, but we're using it to prove relationships between two segments, and that's what this section is about, proving relationship between segments. So somehow we're going to use the segment addition postulate to prove our case here. Okay, well, how are we going to do that? Well, first of all, what does it mean for things to be congruent? So because the segment addition postulate is about segment lengths, right? Look at this. There's no bars over here, like nothing like that here. So segment addition postulate is about length. So we convert all of this information of congruency into segment lengths. Okay, so we know CE, therefore CE is equal to FE. That means this length is equal to that baby length, and ED is equal to EG. We got that. So I converted the congruencies to segment lengths. Okay, so big deal, you say. Well, okay, well, hold on. So here it is. So why is this true? How do I know that CE is equal to FE from this? Well, that's just a definition of congruence. Okay, so definition of congruent segments, basically definition of congruent segments, or you can just say definition of congruence, because it's assumed you're talking about segments. So definition of congruence. Okay, well, what do I do now? Now what I'm going to do is I'm going to start using my segment addition postulate. So segment addition postulate states that you take two baby segments, you add them together, then they'll give you one big segment. So, okay, so I can see over here, for example, that CE plus ED, that's this baby segment plus that baby segment. If you take two baby segments, all right, then that gives you the one big segment, that's CD. So this is true because if E is between C and D, then CE plus ED is equal to the CD, the big segment. So this is because of segment addition postulate. All right, now what am I going to do next? Okay, so now since this is the case, watch this. If CE plus ED equals CE plus ED equals CD, then but I know CE to be FE, I can substitute FE over here in place of CE. Now I also know that ED is equal to EG, so I can substitute EG in place of ED over here. So then what I'm going to do is this, all right? I'm going to substitute FE right here, okay, FE, okay, plus I'm going to substitute EG over here, all right, in this particular statement that I have written. And I'm going to keep this here. So because I'm given this stuff, I took CE and replaced it. I replaced this with this, and I replaced this with sorry, not with that, and I replaced that one with this one. So I do a little bit of replacement, okay? So CE plus ED equals CD, that's because of the segment addition, and here FE plus EG is equal to CD, okay? Now why can I do this? Because of substitution property of equality. This is substitution property of equality. Okay, now you observe, see, FE plus EG, now that's this plus this, correct? Now that's this over here, isn't that like the two baby segment? But before we write that, what we have to say is this. Now watch, we know that FE plus EG is equal to FG, okay? Now why do we know this? FE plus EG, that's because again of segment addition postulate. So I can write this over here. I'm hoping I got the numbers right here. So this is again segment addition postulate. So segment addition postulate, and I got this statement. So I've used segment addition postulate two times. First over here to about this segment, and then I made a cunning trick. I kind of made it look like the other one. I replaced this one with this one and this one with this one, and I got this, and I paused, okay? And then I restate the segment addition postulate with this one over here, okay? Why did I do that? Because then you can see, okay, now FE and EG and FE and EG have two statements over here like this, okay? And this is CD and FG over here, isn't it? I can just do one of these. See, I know CD is all of this, right? So I can replace this whole thing over here with CD, right? Because these are the same. So then I can say CD, right, is equal to FG. Ta-da! It's like a play of hands. It's like, you know, like a magician. Like, you know, well, FE is equal to EG. I'm just going to substitute over here, and I have CD is equal to FG. That's this thing is equal to that thing. Almost there. Almost there. So step number 7, then we can say segment CD is congruent to segment FG over here like this. Oh, I didn't say that over here. This is the substitution property. We can just say property of equality. And 7 over here is definition of congruence. So now look, now what seems like a very intuitive proof, right? We have intuitive thought, and we have proved it in a very logical fashion. Now you might think, why take something simple and make it complicated? It's nothing like that at all, because your mind actually does this in a millionth of a second probably, and then but this is how our thought processes occur. So let me review the proof here again. So we were given that this segment and this segment were congruent, and this segment and this segment were congruent. And to prove, we were asked to prove that this whole segment is congruent to this whole segment. And whenever you see two baby segments, and you can have to start thinking about segment addition postulates. So we're given information, we converted them into equalities because we know a whole lot about properties of equalities, right? And we got that. And then we used the segment addition postulate for this segment, and we said the two baby segments give you one big segment, correct? And then we made a trick. So this was actually the critical step. So we substituted the given information, the two baby segments, and over here, and then I used the segment addition property for the other segment, and then I substituted CD over here to get CD equals to FG, and then by definition of congruence we got what we were trying to prove. Now you kind of have to do this proof several times, all right, like in your mind's eye, and write it down, so until this becomes natural to you, because thinking logically step by step is kind of forcing your mind to a little bit slow down a little bit, and it does take a little bit of practice. All right, let's do one more question before we finish, inshallah. All right, here it is. Here we're given that JL, that's this over here, JL is congruent to KM over here. Okay, then that's interesting. So this is congruent to this. So they kind of overlap, okay? So they overlap. And then we're asked to prove that JK, that's this baby segment over here, is congruent to LM, that baby segment over here. So we got two big segments that overlap that are congruent, and we're asked to prove that the two baby segments here are congruent. Now this may or may not be readily apparent to you as intuitive, but we're going to try to prove it. Okay, so here's a two column proof over here again, and I'm going to write statements here, and here I'm going to write the reasons for my. So, well, when in doubt, you don't know where to start, you write the given. So the given information is JL is congruent to KM. All right, so we got that. Okay, so that's given information. Now, I hope you appreciate by now that that's usually when you're given these congruencies, now we're converting them into, equalities. So here it goes. This means that JL is equal to KM, okay, because why? That's like the definition of congruence. We got that. Okay, what do we do now? Well, we don't know a whole lot about different stuff now, but we do know segment addition postulate with two baby segments give you one big segment. Okay, so well, I know that JK here, if I take segment JK and I add that to KL, and I get the big segment JL over here, don't I? Because how do I know this? That's the segment addition postulate that we just learned. Segment addition postulate. Okay, so that's kind of making progress, right? So we're kind of making progress there. So this baby segment, that's good. So I like what I did, so maybe I will do it again. So okay, I'll do it again for the other one. So I'm going to say KL plus LM is equal to KL plus LM is a big segment KM over there. Okay, now that looks good because I got JL over here going over here, KM over here. So it seems like I'm making progress. So this is from segment addition postulate, applied 2 times to the bigger segments, right? Okay, now what do we do? Well, we're trying to prove that the two baby segments, which is JK over here, and the K and the LM over here, we're trying to prove that those are congruent, right? That's kind of why we kind of want to isolate them together, be congruent somehow. Okay, but how are we going to do this? Well, we know that here we know, see, JL is congruent to KM. Maybe I could just like substitute that into one of these over here. You know what I'm saying? Maybe I could just replace this one over here with KM. Okay, let's see if I could do that. So then I would have JK plus KL is equal to KM over here. Okay, so I just replaced JL with KM over here. So the reason for this would be substitution property of equality. Okay, cool. But now what I can do is see, now I have this and this over here, correct? Now I have this statement here. Watch, I have these two statements. I can combine them. I can combine them either two ways. I can say transitive property because there's something common into that. Because the transitive property, if A equals B and B equals C, then A equals C, right? So that's the transitive property. Or I could just substitute this in place of Km over there. So either one will work because of either substitution property or transitive property. I could say that this over here, KL plus LM, is equal to this over here, which is JK plus KL. All right, so let me just say here substitution property of equality. All right, so I got this. Now what? Now again, I'm trying to prove that JK, this one is equal to LM over there, right? Okay, fine. So well, now I have these two common, right? I have KL over here. I just like cross these off, right? Okay, so then I can say LM is equal to JK, and okay, well, how is that? Because of subtraction property. Subtraction property of equality. Here I should be more precise in this statement before substitution. You should spell that out, right? Because they both sound like subtraction. So now there I am. So JK LM, well technically it's LM equals JK, but everybody knows that if this is the case, then JK equals LM because of not reflexive but symmetric property. Symmetric property of equality. Okay, and finally I can say 8 JK is congruent to LM like this. Okay, and that's because of definition of congruence. All right, now here's a proof that may or may not have been readily apparent to you, but we took two segments, longer segments that were congruent, and then we prove that these two to be congruent, right? Now how do we do this? Because the proof may not have been readily apparent to you, and I must suggest to you, you have to kind of write this down one time or two times or three times if you need to make sure the thought processes flow over here. I'd like to suggest to you also there's more than one way of proving a particular geometric problem, so there could be multiple ways of performing a proof. But here I stated the given information and converted into congruence into equalities, and then I used the segment addition postulate 2 times actually over here to write the 2 baby segments equals to 1 long segment, and then I substituted one of them into the other using substitution property of equality. And then I used a substitution property of equality again to equate the 2 longer segments over here, and I subtracted KL from both sides, subtraction property, to get that, and I used symmetric property. Now these proofs are in the long run actually simple proofs, but you really have to kind of know them backwards and forwards. They will act as a foundation for proofs in the future. So you almost have to do it to the point that you memorize the logical thought processes here for you to be comfortable with them. Now, before we finish, I'd like to introduce something very important to you, and that is, you see a lot of times we were given congruencies over here, and then we convert them to equalities, it's obvious now that if 2 segments are congruent, then they are going to be of equal length. We use this so much that we want to save ourselves some step here, right? Because every time you have 2 congruent segments, we don't want to be replacing that with with equality. So we have what's called a segment congruence properties. So just like we had properties of equality, we have properties of congruence. So we have properties of segment congruence. So, and these you have to know because you already know these, because just like we have reflexive addition property of equality for real numbers, we have reflexive property of congruence, symmetric property of congruence, and transitive property of congruence, all the same properties. That is, this was a reflexive property of equality for real numbers. In the same way, we have a reflexive property of congruence for segments. That is, reflexive property, that's property of congruence for segments. Now, and there's symmetric. symmetric property of congruence for segments. And there's transitive property. RST, transitive property of congruence for segments. Now, the previous properties, there was reflexive property of equality for real numbers, symmetric property of equality for real numbers, transitive property of equality for real numbers. These are reflexive property of congruence for segments, symmetric property of congruence for segments, and transitive property of congruence for segments. So as I said, these recur again and again. So reflexive property of congruence for segments means that a segment, any segment AB, is congruent to itself, like this. That's easy enough. Reflexive property of congruence says for segments says AB is congruent to itself AB. And symmetric property says is if AB is congruent to another segment CD, all right, okay, then CD is congruent to AB, like this. Before, we had a symmetric property of equality for real number. That means if A equals B, then B is equal to A. Same thing here. If AB is congruent to CD, then CD is congruent to AB. Okay, that is the symmetric property of congruence for segments. The transitive property of congruence for segments states that if AB is congruent to a different segment CD, and CD is congruent to a different segment, let's say EF, all right, AB is congruent to CD and CD is congruent to EF, then AB is congruent to EF, like this. That is, if A is equal to B and B is equal to C, then A equal to C. That was our transitive property of equality for real numbers. Transitive property of equality for congruence is very similar to that. If AB is congruent to CD and CD is congruent to EF, then AB is congruent to EF. I just wanted to introduce this, and we shall build on this in the next time. Until then, as-salatu was-salamu ala rasulillah walhamdulillahi rabbil alamin. Assalamu alaikum.